I'm Jaeyeon, and today I'll be talking about our work on the continuous tensor abstraction, where you can access tensor with real numbers. So arrays, which today also tend to be called as tensors, are one of the most universal ideas in computing. We all learned them in our very first programming class, and they show up everywhere, like from scientific simulations to deep learning. And whether it's old languages like Fortran or modern frameworks like PyTorch, they all share the same basic tensor abstraction. And since every tensor lives in integer grid, and this property allows compilers to be really powerful, like they can do loop transformations and auto-vectorization, auto-parallelization, and all the polyhedral tricks. So as programmers, we can just write something very simple, like an einsum, and the compiler can turn this into very fast code that you can run on the hardware. But there's a whole class of applications where these compiler optimizations just don't work. Things like point cloud processing or spatial databases. So these communities have to build their own framework and fragmented libraries built on top of different data structures. So we ask ourselves, like, what makes them different? So one thing we found was these data have coordinates that are real number, not integer. Let's look at convolution as an example. If your data lives on integer grid, you can write convolution in a clean einsum-like form, and the traditional compiler turns that into very fast code. No problem here. Now let's try the exact same convolution, but this time the points don't sit on the integer grid, but they can be anywhere in real number space. And this is what people call as point cloud. And if you want to write a very high performant kernel for this point cloud convolution, in practice you probably have to write like 3,000 lines of code in C++ or PyTorch. Unlike traditional tensors, you now have to decide how to store this data in real memory and how to access those data structures very efficiently on the hardware. And the problem is, none of the existing high-level tensor language compiler can help you here. But here's the key idea. What if tensors could have real value coordinates? Then you can index them with real index and still write the exact same einsum as before, for the point cloud convolution. And now imagine if there's a magical compiler that can take this real index einsum and generate efficient code automatically for you, then the user can now write the same simple high-level tensor expression as before, nothing new to learn, but under the hood, everything works for the real coordinates. This is exactly what we are doing in this work, and we call such model as continuous tensor abstraction. From now, I'll explain a continuous tensor and the language we use to express computations, which is einsum. And then I'll walk through how we can compile these einsums into efficient code, and finally show some evaluation results. Let's first talk about what we mean by continuous tensor. Previously, when people talk about tensor, we usually imagine something like integer grid, like pixels. But what if we remove this grid? Now your data no longer has to sit on integer grid, but can live at any real number domain. So you can think this tensor as mapping from real to value domain. So in this figure, in this particular figure, any x, y coordinate that falls on the blue pinpoint has some value. Otherwise, the white regions represent zero value. Of course, if we go all the way to like full generality, things can be really messy. So you could have tensors like this divided by really irregular and complex boundaries. And when we try to multiply these two tensors, we have to find where those boundaries actually intersect. So this can lead us to like root finding problems and handling all sorts of numerical edge cases, not something we want to wrestle with. So in this work, we take a more structured approach. It's still continuous, but designed to be much more practical. So we focus on piecewise-constant tensor. And the nice thing is the many applications I mentioned earlier can perfectly fit within this model. So when we say about piecewise-constant tensor, first, it is consisted of finite number of pieces. And each piece holds a constant value and is an axis-aligned box with any real number boundaries. And the entire pieces cover entire region without overlapping each other. And the fun thing is, even with this structure, we found that we can still do a lot of interesting things. Starting from the previous example, you can represent boxes by assigning non-zeros to the interested box, like piece 1 and piece 4 here, and zeros elsewhere. You can do lines similarly, and of course the point clouds as well. And now let's talk about the language we use to describe computations on these continuous tensors. We extend the familiar Einsum notation, except now the indices in Einsum can be real, not just integers. So for example, I prepare here element-wise multiply between two continuous vectors. This looks exactly same as the standard Einsum, ax times bx. The only difference is that the index x is now a real variable. And you can also do multidimensional broadcasting element-wise multiply like axy times bx directly on 2D continuous tensors again. And one important difference between traditional Einsum and continuous Einsum is that how reduction works on continuous domain. So let's say we have 3 non-zero points in a continuous vector like this, and we just want to sum them up. And in order to do that, we simply add their values together, just like in discrete case. On the other hand, let's say if our user has a 1D continuous vector, but now with an interval. So value is 3 across the range from 0.9 to 1.8. And if the user wants to multiply this value 3 with its interval length, this means integral. So in our language, we need to distinguish between these two reduction modes, summation versus integration, depending on what the user actually needs. So in our Einsum, we designed to let the user explicitly specify which measures to use for each reduction variable. So if you want summation, user should mark that variable with the counting measure mu sharp. And if you want integration, you mark it with a Lebesgue measure mu lambda. So in other words, you can think the measure acts like a signal, tells the compiler how to reduce along that axis. In general, our continuous Einsum language takes following form. The notable difference, again, shown in blue, the user specifies a measure for each reduction index. And on the middle expression, the main expression can include tensor access with affine indexing and a variety of arithmetic operations. Now let's move on to how we implement continuous Einsum efficiently on the real hardware. And because our tensors are piecewise constant, we can specialize the implementation using this property. So let's walk through an element-wise multiply example again. The first step for the implementation is to partition the iteration space into regions where both tensors A and B are constant. So you can see in the middle, the space is now partitioned into 6 regions, each formed by the intersection of pieces A and B. Next, for each partition, we evaluate the Einsum expression. So since both tensors are now constant in that region after the partitioning, all we need to do is just compute that expression with constant values. And here I prepare the pseudocode of the implementation for this Einsum. To partition the iteration space, we can check all pairs of pieces from A and B and find their intersection. And then we evaluate the constant expression for each partition. And this all pairwise comparison works really well to figure out the partition, but this can be really expensive, quadratic in number of pieces. So one key optimization is that we don't actually need to compare all of these pieces. Instead, we can partition the iteration space much more efficiently. So we can use a 2-finger merge technique. By walking through the pieces in sorted order, we can avoid unnecessary comparison, and algorithm now becomes linear. And what we found was, in reality, a lot of piecewise tensors have a large amount of 0 pieces. So by skipping those with a sparse intersection approach, we can avoid doing wasted more further. And now this makes the complexity depend only on the number of non-zero pieces instead of the full sizes. So to summarize, we extend Finch, which Willow introduced earlier in this session, and to a compiler that can take arbitrary continuous line-sum expressions and generate very efficient kernels. And if you're curious about how, like, the memory layout for the multi-dimensional piecewise constant and how we extend Finch and how we handle continuous reduction, please see the details in the paper. And now let's move on to the evaluation. We will start by showing you one of our applications, a radius search query. This is simply asking, given a circle query, which points lie inside the circle. And we formulate this problem as an element-wise multiplication between two-dimensional tensor. The point cloud tensor points x comma y, and the box tensor box x comma y. And each blue points in the red box carry value 1, while the other white regions are 0 valued. So as a first step, we first place the bounding box of the circle in the red box into the piecewise tensor representation. And then we apply a mask using a circle condition. So this condition acts like a filter, so only the points inside the circle will eventually remain. And then we compare our generated kernel of that einsum with Shapely, a state-of-the-art geometric library. And we see that we got like huge speed up compared to the Shapely. This was mainly because Shapely is optimized for box queries. So for the circles, they also have to materialize all the candidate points within the bounding box, similar to what we did, and then filters them in the second pass. In contrast, our compiler fuses everything into a single pass, so avoiding unnecessary materialization. What's so powerful here is that our model can naturally express many applications that are very hard to write in simply in traditional tensor languages. So from geometric queries like radius search query or box search query to interval joins and all the point cloud convolution, each of these can be written in continuous einsum very concisely with just 1 or 2 einsums. And across a lot of applications, our compiler can achieve comparable or better performance than handwritten libraries while reducing programming effort a lot. So when you look at the point cloud convolution case, we found out we can save up to 100x fewer lines of code with better speed. And I want to conclude with this slide. And tensors and geometry, two worlds rarely talk to each other previously, but we believe this work can act as a bridge so that even non-tensor world programs can be explained in tensor terms. So we introduced einsum concepts and sparse tensor optimization concepts to the non-tensor world. And we believe different direction can also be a very interesting future work. So can we leverage ray tracing core in modern GPU or spatial data structures like bounding volume hierarchies for tensor computations? And I hoped you enjoyed the talk and happy to take any questions.
Hi, nice talk. I have one question. Given that you use constant values to do the tensor computation, is there any trade-off? I mean, between the performance and, for example, precision or... You mean the piecewise constant tensor only? Yeah, right.
Yeah, that's one of our design choice because when we, let's say, that's for the performance trade-off because we could have the value to be more complex arbitrary function using symbolic engine, but that can take the performance really bad in some cases. So we want to keep the simplest possible. So we only store the scalar value. And in most cases, we can represent many applications, even with piecewise constants. Okay. But that's our future work.
Okay, thank you.
Hi, great talk. I see that you extended einsum notation with affine operations for convolution. and that's very cool. Have you considered other extensions, or would it even make sense, like tensor concatenation?
Oh, we can think about concatenation between we can think about continuous support for the concatenation.
Like a sum of 2 point clouds, in a set theoretic sum of 2 point clouds.
Yeah, concatenation can be represented as a affine index, and I believe Finch can already support concatenation. So we haven't tested it, but I think we can already support concatenation since we can support affine index.
Thank you.
Yeah.
Okay, for the sake of time, we have to stop the session now. If you have any other questions, please find the speakers afterwards. Thank you.